So, our first shortcut for differentiation is the power rule. And what you could do is you could use the definition of the derivative and figure out all of these one by one, and you would find out the following. X squared wouldn't be too bad with the definition of the derivative, and you would get 2x. And x cubed would be a little bit worse, and you would find out that it's 3x squared. And x to the 4 would be a little bit worse than x cubed, and you would find out that the derivative is 4x cubed. 3x cubed wouldn't be too bad. And so we start to see maybe a pattern. X to the negative 2, that's like 1 over x squared, becomes negative 2x to the negative 3. And 4x to the negative 3 becomes negative 12x to the negative 4. So can we see a pattern? What's happening? If you've seen the pattern before, that's not allowed to see the pattern again. So take a look. It's still the same pattern that you saw before. That is true. Looks like you're timesing the coefficient by the exponent. So all these ones have a 1 in front, right? Yeah. So now I have a 2, a 3, a 4. And here I have a 3 in front, and it's getting multiplied. So that exponent seems to be coming out in front and multiplying. Does that even work for this one? Sure enough, 4 times negative 3 is negative 12. So that explains the number in front. And that is true for this shortcut. Your exponent will come out in front and multiply by whatever the coefficient is there. The next thing we have to figure out is what happens to the exponent. It's 1 less. So it was a 2, now it's a 1. It was a 3, now it's a 2. It was a 4, now it's a 3. It was a negative 2. What's 1 less than negative 2? Negative 3. So the power rule says, well, here's some more. Now they get a little bit tricky. We're going to do that same idea where we bring the exponent out in front and do the exponent 1 less. How are you going to do the square root of x? I'm going to put an extra equal sign in here between. Can you write that as a power? What's another way of writing the square root of x? X to the power of 1 over 2. And it even works with fractions as exponents. You can bring that fraction in front, or that number in front, so it'll be 1/2 in front. And what happens if I subtract 1 from the exponent? I get negative 1/2. It even works with numbers. I mean, 5, if I wanted to, I could write this as 5x to the 0. Now, you're never going to do that, but you could. Because what's x to the 0? It's equal to 1. And that would be 1 times 5. Now, if you brought the exponent in front, what's 0 times 5? It's going to be 0. So, in fact, the derivative of any constant number is going to be 0. 7x to the 1. Well, if you multiply the 1 in front, you're going to get 7. If you subtract 1 from the exponent, you're going to get x to the 0. But we're not going to write it like this. We're going to just write this as 7. Does that make sense? And then x to the cube root of x, you can write as x to the 1/3. So the 1/3 comes out in front. And in this unit, you're going to get really good at subtracting 1. It's not a very hard skill, but you're going to get good at it. What's 1/3 minus 1? negative 2/3. So now we have 1 over the square root of x. How do you write that as a power? Well, we could start by saying, since we know the square root of x is x to the half, we could say this is 1 over x to the half. How can I write that as just x to the something? What do you do with powers on the bottom? If you put them on the top, they become negative. So 1 over the square root of x is equal to x to the negative 1/2. And now if we do the same pattern, the negative 1/2 comes out in front. And now we subtract 1. Negative 1/2 minus 1 is negative 3/2. So in general, we have the following rules. We have the constant rule, which means if you have any number just by itself, the derivative is going to be 0. And we saw that when we took that number and made an x to the 0 after it. You're basically using the power rule to say that. But any plain number by itself, the derivative is going to be 0. Then the power rule is exactly what you saw before. Whatever your exponent is. So here I have an exponent of n. That comes out in front. And then in the exponent, you subtract 1. So the number comes out in front, and then you subtract 1 from the exponent. And we also saw if there was any number in front to begin with, then it just multiplies by that number. Now, a little bit of extra math terminology here. This works for all real numbers n. So you can have fractions, you could have square root as an exponent, any kind of regular real number this works for. Now, in brackets here, this is mathematical shorthand. Some of this you've seen before, right? You've seen that this means all real numbers, right? And you've probably seen this before, mainly with x, right? When you're doing domain questions, you might have, in short form we say XER, but it's not actually XER. This is the math symbol for sometimes when you're reading it, you can say belongs to. The reason it kind of looks like an E because another proper way of saying that n is an element of the real numbers, meaning it belongs to the real numbers. And here's a new symbol that you've never probably seen before in math. For whatever, mathematicians, when they have to say things often, they get tired of saying them often, and so they create a symbol, so it takes less time to write it down. So like all real numbers takes a long time to write down, so they make a special R for that. The upside down A means for all. That doesn't take that long to write, but I guess if you have to write it often enough, you're like, okay, we'll make up a new symbol for all. My favorite one in math classes in university, thank you, was if. That means if and only if, the extra F. So in mathematical proofs later on, you have to write these things down, and sometimes you want to say this is true if and only if this is also true, but you get tired of writing if and only if, so then you write if with 2 F's. So there's a bunch of these mathematical things that come up. I'll just introduce you to a couple here today. So that's what all this extra stuff is. Do you need to know that? No. Will I ask you to write it out with mathematical shorthand? No, but maybe it's interesting. And this is what happens if you have anything, any number in front of any function, then that constant just stays there. So what they're trying to say in this constant multiple rule is if my function looks like this, y equals 6x to the 8. Well, my 6 in front is a multiple. So I can, when I'm figuring out my derivative, I can keep that 6 there and just do the derivative of x to the 8. What is the derivative of x to the 8? Well, it's 8x to the 7. 8 comes out in front, and you subtract 1 from the exponent. Of course, you're going to skip that step because you're just going to say, I'm going to bring my 8 in front. What's 8 times 6? 8 times 6 is 48. Subtract 1 from the exponent, and you'll get 48x to the 7. But what this constant multiple rule is trying to say, that if you have a number multiplying in front of any function, it doesn't affect doing the derivative. You can still do the same rules that you had before, which means bring the number in front, subtract 1 from the exponent, since that's the only derivatives rule we've learned so far. Over the course of this unit, we're going to learn a lot of derivatives rules. How do we do different kinds of functions, not just functions with powers? What about sine? What about cos? What about logarithms? What about e to the x? What about cosecant and cotangent? So all of those different functions, we'll be able to figure out the derivatives for them. So here's one for you to try. And how did you do? dy dx, negative 15 x to the 4. Good? Would you rather do that one with the definition of the derivative? Right? If you think about how long that took you, right? What does the definition of the derivative look like? Well, you would have the limit as h goes to 0 of f of x plus h, so you would have negative 3x plus h to the 5 minus f of x, which would be minus negative 3x to the 5 all over h. And all you would have to do is expand an x plus h to the 5, which is x plus h times x plus h times x plus h times x plus h times x plus h. Or maybe you have Pascal's triangle to help you. But it's going to be huge, right? It's going to have 6 terms once you simplify it. Then you have to subtract everything, factor out the h. This is a lot faster. Here's a medium one. And with these questions, you're seeing that I'm introducing different terminology. So here I've got differentiate this with respect to x. Any of these ones that don't introduce a derivative, you can just go and choose one of them, either y prime or f prime of x or dy dx equals. Doesn't matter which one. Now, before I write out the answer, I'm going to take my original function and I'm going to move that x to the 8 to the top. So an x to the 8 on the bottom of your function is like an x to the negative 8 on the top of your function. And this will allow you to do the power rule. So the power rule only works if you have a power in your numerator. It doesn't work if you have your power in your denominator. So once I've brought that up to an x to the negative 8, now I could bring that negative 8 in front. Negative 8 times 3 will be negative 24. Subtract 1, and you get x to the negative 9. It's still divided by 4. If you wanted to simplify this, so that's a medium one because we have to do sort of a preliminary step. We have to manipulate our original function so that it gets into a form that we can do our power rule. So our power rule only works if that power is in the numerator, and then you can work from there. This one's not a hard one, but again, I'm just introducing some more terminology. So when you have a d dx in front of a function, that means find the derivative of whatever's inside. So if I want to find the derivative of what's inside I could write it like this. The derivative of 7x to the 4 is, bring the 4 out in front, subtract 1 from the exponent, 28x cubed. More specifically, it's not only finding the derivative, but it's finding the derivative with respect to x. Because you could find d dy or d dA or whatever variable you wanted. And sometimes later on, we're going to find out we have some equations with multiple variables. But we'll only want to find the derivative with respect to one of those variables. And this is the hardest one at this level so far. Again, we need to have and change that so that it's a power in your numerator. So while you're working on it, I will put it up here so you can check afterwards. So the cube root would be an x to the third. So the fact that there's a cube root of x squared, the cube root of x squared is x to the 2/3. But because that's on the bottom of my fraction, if I move it to the top of my fraction, I have to use my negative exponent laws, and that becomes x to the negative 2/3. So once I've changed it to that form, I now can bring the 2/3 out to the front of my fraction. That'll give me I just multiplied by the 7. If you wanted to bring the 2/3 and multiply right by the 7/3, that would work as well. Depends how you see that number in front. So I looked at it as just doing the top and keeping the 3 on the bottom. That's fine. You could have also looked at it as a 7/3 in front. And if you multiply 7/3 by negative 2/3, can you see you'd get negative 14/9 right away? Which might be a little bit faster. It is a little bit faster. But just showing that either way would work. Subtract 1 from the exponent. Negative 2/3 minus 1 is negative 5/3. See how in this way, the reason I did this way, I wanted to think about how do we work with fractions. I could think of this 3 on the bottom as 3/1. And if I have a fraction divided by a fraction, I multiply by the reciprocal. So then I can think of this as multiplying by 1/3, and that would give me my negative 14/9 as well. last two examples. If you're told the derivative is 5x to the 4, what would the original function have been? Yes, an x to the 5. And if you were told that your derivative was 12x squared, what would your original function have been? Okay, so if you're working through this, some of the things that you would have done, okay, when figuring this out, what always happens to the exponent? You always subtract by 1, right? So that would tell you right away that this one has to have an x to the 3. And then, well, the number in front, when the 3 comes out in front, has to make 12, so that means that that number in front would have had to have been a 4. Okay, I'm going to give you guys about 10 minutes right now to work on some of these, and then we're going to do the next little section of notes, which isn't very long, and there'll probably be about 10 or 15 minutes at the end of class to work on that section of homework as well.